Hello, my name is Duk-Min Vo, from the University of Tokyo. Today, I'd like to introduce our paper entitled Anticipation Captioning with Commonsense Knowledge. This is a joint work with Kwok Luong, Professor Akihiro Sugimoto and Professor Hideki Nakayama. We're curious if, given a sparsely temporally ordered set of images, we are able to create a caption for an unseen image that is the future of seen images. As a result, in this study, we explore a novel image captioning, namely anticipation captioning. We propose to generate a caption because, first, we may learn from the success of image captioning, which has a variety of uses. Second, we can easily leverage recent advances in text-to-image or text-to-sound as a flexible transformation that will benefit other downstream tasks. We hope that our work will open the way for a variety of applications such as incident prevention. We propose a baseline model, called a CAP, which incorporates common sense knowledge into a pre-trained vision and language model. In our task, the input is a sparsely temporally ordered of images. For reference purpose, we assume that an oracle image is the future of the seen images. Our task is to generate a caption for the unseen oracle image. We compare the outputs of different image captioning tasks. The generic image captioning and storytelling tasks generate captions for the seen images, while our anticipation captioning task anticipates what happens afterward. We hypothesize that under common thinking, the future can be predicted from observable concepts such as objects, events that appear in the input image. In addition, the future will not dramatically change. For example, the future cannot change to the football scene from the hockey scene. As a result, we make full use of common sense knowledge to connect all detected concepts in terms of a graph while expanding the graph toward forecasted ones, creating a knowledge graph. The term forecasted concept refers to a concept that isn't visible in the given image but related to another concept visible in the image. Now we'll explain our proposed method in detail. We first use object detection to detect top 10 concepts for each given image, and using ConceptNet, we use each detected concept as a query to heuristically retrieve forecasted concepts with 2 hop neighbors of the query. We perform the filtering process to remain 60 forecasted concepts. If 2 concepts are related in the ConceptNet, we connect them by an undirected edge. Finally, we obtain a knowledge graph for the next step. At the same time, we also extract image features. Next, we use an attention graph network to update the node embeddings through iterative messages passing between neighbors on the graph. The initial embedding of each concept is obtained using the pre-trained language model. To strengthen the connection between concepts and image context, we concatenate the node embedding and the context feature, which is the average of all image features from the pre-processing step. Finally, we use the concept embeddings learned from the graph neural network are used as a prompt to generate the caption. In particular, we inject all concept embeddings into a frozen pre-trained VinVL. Following previous works, we simply use cross-entropy between the generated and the ground truth captions to train the network. We use the visual storytelling dataset, VIST, with a modification to evaluate our method because there is no dataset tailored for our task. We use the first 4 images of each sample as input and the last sentence of each sample as the ground truth caption. We keep the last image of each sample as an oracle image for reference. The training, validation, and test sets all have the same number of samples as the original dataset. We carefully design methods that can be straightforwardly applied to our task. For a fair comparison, all compared methods are fine-tuned on VIST. To avoid overtuning, we only train the methods for a few epochs and select their best checkpoints. Comparing our method to cutting-edge image captioning VinVL will demonstrate the advancement of our method over the conventional image captioning model. VinVL plus oracle image is the method where VinV loses the ground truth oracle image in training and testing. We may regard this method as a method that sequentially generates the oracle image and caption. AREL plus BART is a combination of visual storytelling and story ending generation. We compare the ending sentence to the caption by our method. We show some randomly selected examples of captions generated by our method as well as others. We can see that the captions generated by VinVL are completely out of context with the input images. This observation suggests that the current image captioning model is inadequate for our task. VinVL plus oracle image generates reasonable captions to some extent when the oracle images are close enough to the input images. We notice that AREL plus BART generates a general ending for the story. On the contrary, our method produces more accurate and reasonable captions that reflect the input's future. In most cases, we can see that our method accurately predicts what is likely to happen, which is classido the ground truth captions. To have a better understanding of the generated captions, we use the Stable Diffusion model to generate an image from each generated caption. The images obtained from our generated captions are similar to the ground truth ones, indicating that our method generates correct anticipated captions. The quantitative scores are summarized in this table. We first assess all methods based on their accuracy. All of the results in this table support the advantage of our method over the other methods. The descriptiveness of generated captions is then assessed using a self-retrieval strategy. In comparison to VinVL and AREL plus BART, our method outperforms them significantly. This is thanks to the fact that captions generated by our method are close to the ground truth images, whereas those obtained by the other methods are not. Our method and VinVL plus Oracle image achieve the same level. This is not surprising, given that VinVL plus Oracle image generates captions directly from Oracle images. When we simplify the model, the performance scores are degraded. In the case of a cap without GNN, the concept embeddings are insufficient to guide the model to generate the expected caption. As a result, the caption most likely describes the input. Similarly, a cap without context breaks the connections between concepts and the context of images in general, resulting in captions that are far from the inputs and similar to each other if the detected concepts are similar. In contrast, the full model generates plausible caption. Here we show an example of knowledge graph obtained by our method. We see nodes in the graph are densely connected, meaning most nodes are related. We remark that the number of nodes is 100 and the number of edges is 6,000 on average. Here is the portion of the knowledge graph that is extracted using only the forecasted concepts, brown nodes, appearing in the anticipated caption, and the detected concepts, blue nodes, related to the forecasted ones. We can see that our method successfully retrieves forecasted concepts from ConceptNet, which are the future of detected concepts. More importantly, our method can include forecasted concepts in the final caption thanks to our usage of prompt learning. Finally, we notice a relatively small number of samples with low scores when delving into each sample in detail. Here we show an example of failure, because in this case, the scene shifts from wedding to night time, which contradicts to our hypothesis. Our method cannot predict the caption correctly. We will further investigate this issue in our future work. In conclusion, we propose a new image captioning called anticipation captioning and provide a baseline model for this task. We look forward to discussing with you at the poster session on Wednesday, morning time, poster ID 247.